All right, we're going to talk about limits algebraically. Let me make this a little bit less blurry. All right, there we go. So you can see my limits algebraically here, and I'm going to bring up the classwork that I handed out, and we're going to do the problems together here. And I'm going to work them on a separate sheet of paper here. So number one, the limit as x approaches 1 of 5x to the 8th minus 3x squared plus 2. Okay, and I have the list of things to try that I put out on a card here. So we substitute first if we can, and we can put a 1 in here. So it's going to be 5 minus 3, which is 2 plus 2, and then this is 4. So let's make sure I added that right. 5 minus 3 is 2. 2 plus 2 is 4. So on the very first one, we could definitely substitute. All right, number 2 is the limit as x approaches 3 of x squared minus 1 over x minus 1. Now this one looks a little bit trickier because, you know, you got a denominator and you think maybe you might not be able to substitute. But in this case, we're approaching 3. So this function has a problem when x is 1. So I can definitely substitute into this one as well. So x squared, if I use substitution, is 9. 9 minus 1 is 8 over 3 minus 1, which is 2. And then that's also 4. No coincidence, right, that the first two are 4. This 9 minus 1 is 8, and 3 minus 1 is 2. Yeah, that works. Okay, number 3, the limit as x approaches 0 of x squared plus 2x over x. As x approaches 0. Can I plug a 0 in here? No, so substitution doesn't work, so I've got to use some algebra somehow to eliminate my domain problem. And in this case, I notice right away I can factor out an x out of the numerator. So we get the limit as x approaches 0 of x times x plus 2 all over x, and this is canceling, and then I'm left with the limit as x approaches 0 of x plus 2. And now I can go back to step 1, which is substitute, and plug in x equals 0, and I get a 2. Which means graphically, this is a removable discontinuity at the point 0, 2 for this graph, which is pretty cool. All right, number 4, the limit as x approaches 2 of 4 minus x squared. And this is over x minus 2. Now I try my first step, which is substitution, and I can't because I'll have a domain problem in the denominator. And now I have to think of some algebra, if I can, to see if I can eliminate the domain problem. And I notice that this numerator does indeed factor, so let's try that. The limit as the difference of squares. So this is going to be 2 plus x and 2 minus x over x minus 2. Which is not necessarily helpful because these are opposite signs, SIGNs. So what I'm going to do is I'm going to factor a negative out of either this term here or this term. It doesn't matter which. So I'm going to be a little bit ornery and factor it out of the top one. And that makes this x minus 2, right? Because I flipped the signs. If I factor a negative 1 out of this, it makes this negative 2 and this a plus x. So I'm just going to change its direction or its orientation there. So I'm going to cancel now, and then I'm left with the limit as x approaches 2 of negative 2 plus x. And now I can plug in the number 2 using substitution, and that's going to be 2 plus 2, which is 4, but this is negative 4. All right, running out of paper space in the view. So now we're going to go to number 5. Number 5 on the screen is the limit as x approaches 3. This is an arrow, by the way, of x cubed minus 27 over x minus 3. And then you have to decide, well, can I substitute in? The answer is no, because if I put a 3 in the denominator, I get a 0. So I've got to do some algebra. And yes, this is the difference of cubes up here in the numerator, so I can indeed factor that. And I just want you to remember, this is the same, opposite, always positive, or, you know, the grape and the seedless watermelon, however you might have learned it. And I like to think of the difference of cubes as what am I cubing here? Well, you're cubing x, so that goes here. What are you cubing here? Well, you're cubing -3, so that goes here. And then what do you multiply by x to get x cubed? Well, x squared goes here. And then what do you multiply by -3 to get 27? Well, a +9, you see. And so you've got it almost filled in. And then the middle, what do? You just multiply these two together. And you get 3x. But it's same, opposite, so this has to be positive, always positive. All right, and then our term cancels, and we're left with the limit as x approaches 3 of x squared plus 3x plus 9. And now I can substitute. So I'm going to get 3 squared, which is 9. 9 plus 9 is 18. Plus another 9 is 27. All right, number 6. Limit as x approaches -4 of 1 minus 6x raised to the 3/2. All right, let's see if we can substitute in. What happens when I plug in a -4? We get 1 minus a minus 24. So then this becomes 25 to the 3/2, which is the square root of 25 cubed. Well, what is the square root of 25? Well, that's 5. 5 cubed is 125. A nice review there of our properties of exponents. All right, moving right along. I gotta have a divider just to keep me straight here. Okay. Now we're on number 7. We're moving right along. All right, number 7. This one is the limit as x approaches 5 of the log base 3 of 2x minus 1. Now let's see if we can do some substitution. What happens when I plug a 5 in here? I get 10 minus 1, which is 9. So then this becomes the limit. Well, actually, once I take x to 5, I don't need the limit, right? So this is going to equal log base 3 of 9. And this is a log. So what happens is this is an exponent. What exponent do I raise 3 to get 9? Well, you get 2. The answer to that one is 2. All right. Number 8, the limit, as we were spoiled. We got 2 in a row that were substitution. Woohoo! So 3 over x minus 3. All right, so these are my steps. I'm going to put them over here now. So my steps are to substitute if I can. Well, I can't plug a 3 here. That makes it undefined. Then I'm trying to do some algebra maybe to eliminate the domain problem, but I can't factor anything. I can't expand. I could try to use the conjugate, but that's still going to leave a 0 in the bottom. And this isn't a trig one, so I can't use identities. So step 3 means I have to graph it. All right, so let's graph it. Oh, but Mrs. Muller's a rational function. I haven't done it in 100 years. I know. Well, the thing about calculus is that you use everything you ever learned in Algebra 1, Algebra 2, and Honors Pre-Cal, and what you used in geometry, believe it or not. All right, so 3, I have a vertical asymptote. Boom, there it is. And now I'm going to plug in a point. Plug in 0. My horizontal asymptote is 0 because the degree of the numerator is 0. The degree of the denominator is 1. And if I put in a very large number, like a million, 3 over a million is small. So it's going to 0 at the end. Now plug in a 0 to find out if I just need 1 point. And I get -1. So 0, -1. I'm going to put right about here. So I know this part of the graph looks like this. And the multiplicity of the 0 here in the denominator is 1. So I'm going to pass through infinity and come out the other side. There we go. So the limit of 3 over x minus 3 as x approaches 3 from the plus side is infinity. Number 9, the limit as x approaches 4 pi over 3 of the sine of x. Well, this one is a direct substitution, and yes, it's my sneaky top secret way of getting you to try to remember the unit circle. So the sine of 4 pi over 3 is the answer. You're like, yeah, right. Well, okay, that is a number. There is a value for that. And the reference angle here is pi over 3, and the sine of pi over 3 is root 3 over 2. And so we have to decide what quadrant this is in. It's not 1, it's not 2, but it is 3. So this is going to be negative root 3 over 2. Because let's think about it. 4 pi over, this is 1 pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. So it's down low. So the signs or the y's are all negative down here, okay? All right, number 10. The limit as x approaches 4 of the square root of x minus 2 over x minus 4. Now, you could use the conjugate here, and it would not be wrong at all, but I would like you to think about the denominator actually being the difference of squares. You're like, what? Yeah. What are the factors of x? Oh, well, Mrs. Muller hadn't thought about that. You're right. Well, it's the square root of x and the square root of x, and the factors of 4, 2 and 2, and then that's going to be, one's going to be plus and one's going to be minus. And do you see how that really here, x minus 4, is the difference of squares that you really didn't think about? All right, so I'm going to get rid of this factor and this factor. The limit as x approaches 4 of 1 over the square root of x plus 2 equals, now I can go back to my substitution. And I take the square root of 4, and that's 2. So the square root of 2 plus 2, square root of 4, I'm sorry, is 2, plus 2 is 4, so it's 1/4. All right, I think I can get one more on this page. So I'm going to the back of our document. Number 11. The limit as x approaches 0 of tangent of x over x. Now I cannot plug in 0 here because I have a domain problem, but I can change tangent. Now I want us to remember that we are on the lookout, right? We're going to be looking for the limit as x approaches 0 of sine x over x. And we know that's 1. And believe it or not, I know in tangent there's a sine embedded in it. So I'm going to say this is the limit as x approaches 0 of sine x over cosine x all over x. Now this x right here is really over 1. And so what do we do when we divide two fractions after we have a heart attack that we have a double-decker fraction? Well, we copy the numerator, change it to multiplication, and flip the denominator. And there, my friends, has arrived on the scene at the sine x over x. So this is the limit as x goes to 0 of, I can rewrite this as sine x over x times 1 over cosine x. Because multiplication allows you to change the order. It doesn't matter. It's commutative. And now we know that this limit here is 1. And so this becomes the limit as x approaches 0 of 1 over cosine x. Now we could change this to secant if you wanted to be fancy, but we don't have to because now we can plug 0 in for the denominator and we get 1 over cosine of 0. Cosine of 0 is 1, so this turns out to be 1. All right, we're moving along at quite a great clip here. I like that. Number 12, the limit as x approaches 0 of, I think that's, yeah, okay, 3x plus sine x over 2x. Limit as x approaches 0. Now, We cannot substitute here. We would like to maybe substitute, but we can't because I can't plug a 0 in the denominator. Some algebra. I can do some algebra here, but it's not what you think. I'm going to, since I have a fraction, I'm going to bust it up into two things. I can say 3x over 2x plus sine x over 2x, right? Because if I was adding 3/4 to 1/4, that's the same thing as saying 3 plus 1 over 4, right? You know, if I said 3/4 plus 1/4, that's the same thing as saying 3 plus 1 over 4, right? Because they have the same denominator. So all I'm doing is I'm undoing, finding a common denominator, or, I'm busting up the fraction. And you can do that when you have a singular denominator, okay? So I call that the celebrate factor, like celebrate good times, come on. That's what you do when you have a singular denominator and you can bust it up. And again, I can simplify this. The limit as x approaches 0 of these x's cancel, and I'm left with 3/2 plus, now I can say that this is 1/2 times the sine x over x, because this has arrived on the scene now, our favorite limit. We know as x approaches 0, this limit is 1. And so we can say then the limit as x approaches 0 is equal to 3/2 plus 1/2, which is 4/2, which is 2, which is pretty cool. All right, number 13. Now 13 I did in class, but I'll do it again just to make this video complete. This is 1 over 3 plus x minus 1 over 3 all over x. As I have mentioned before, teenagers are allergic to fraction, but doubly allergic to double-decker fractions. So what I'm going to do is have us recognize this is over 1. And what do we do when we have a fraction? We take the numerator, change it to multiplication, and flip the denominator. Now, I like to put the 1 over x in front. It doesn't matter. And then this is the numerator. And I cannot substitute here again because I have a 0 in the denominator. So I've got to do some algebra, right? Use some algebra. So I am going to find a common denominator inside the set of brackets there. And that common denominator is going to be 3 plus x times 3. And I'm going to multiply this fraction by 3, which would be 3. And this fraction by 3 plus x. So it's going to be minus 3 plus x. Please note, we have to use parentheses here because we have to distribute this pesky negative. All right, and then something wonderful happens. We get 1 over x times 3 minus x all over 3 plus x times 3. And the 3's cancel, which is nice. And we can say the limit as x goes to 0 of 1 over x, and I get in brackets here, negative x over 3 plus x times 3. Now you might ask, why, Mrs. Muller, are you not distributing this? Well, I'm not distributing this for a reason, and the reason is that this x is eventually going to go to 0, so that's a wasted effort to multiply that out, okay? So here we go. The x's cancel. I'm left with a negative 1 in the numerator, so this is negative 1 over 3 plus x times 3. And now I can use substitution and put 0 in the denominator, and I get negative 1 over 3 times 3, so it's negative 1/9. All right, number 14. The limit as x approaches 0 of sine of 2x over x. Now we did this in the notes, and I hope you guys all realize that this is just 2. But if you didn't, we could use the identity for the double angle of sine. With the sine 2x is equal to sine 2 sine x cosine x over x. And then I see my miracle, the limit as x approaches 0 of sine x over x times, well, what's left? 2 cosine x over 1. And this we know is 1. And I get the limit as x approaches 0 of 2 cosine x. And now I can plug in 0, and the cosine of 0 is 1, so it is indeed 2. So this, we did this graphically in class, but we can do it algebraically using the trig identity there for the double angle. All right, number 15. Gonna have my separation here. Number 15. It looks like a 16. Let's make it a 15. Number 15, the limit as x approaches pi over 2 of 1 minus sine x over cosine x. Now, the cosine of pi over 2 is 0, so I can't have a 0 in the denominator. Now, back when we were doing trig identities and we wanted to change things around, we used the conjugate with trig functions. Now the conjugate here, I'm going to multiply by a favorable factor of 1, and that factor of 1 is going to be 1 plus sine x over 1 plus sine x, because that's 1, but it's going to make it the difference of squares factors in the numerator. So this is the difference of squares factors. So that's going to end up being 1 minus sine squared x over cosine x times 1 plus sine x. Now, why did I do that? Well, I did that because I need to eliminate the cosine in the denominator because I can't plug in a pi over 2 into cosine and not get 0. Okay, so, and then what happens? I know that the identity for 1 minus sine squared is equal to something. Yeah, I heard it. I know you guys were screaming it out from the crowd. Cosine squared x is equal to 1 minus sine squared x. And I have a cosine x in the denominator, 1 plus sine x. And then I can eliminate one of these and one of these in the numerator, and I get the limit as x approaches pi over 2 of cosine x over 1 plus sine x. And now, may I plug in pi over 2 in the denominator? The answer is yes. And it almost doesn't matter because the numerator is 0. So this is going to equal 0 over, the sine of pi over 2 is 1, so 0 over 2. So this limit is actually 0. But we couldn't use substitution because we were going to put a 0 in the cosine here and have a 0 in the denominator. And then number 16. The limit as x approaches 0 of x over the square root of x plus 1 minus 1. What I'm going to do here is, let's see, can we plug in using substitution? Let's see, can we substitute? I plug a 0 in, I get square root of 1. 1 minus 1 is 0. Nope, can't do it. But the visual clue that you're going to use the conjugate is the square root. So we're going to do the square root of x plus 1 plus 1, square root of x plus 1 plus 1, and we get the limit then as x approaches 0 of x times the square root of x plus 1 plus 1. Now, why don't I multiply this out? Well, because I know I'm going to let x go to 0, and it'll make it easier if I don't. Now, since I use the conjugate, this makes these the factors of the perfect square. Difference of squares. So this is going to be the square root of x plus 1 squared, which is x plus 1, minus 1 squared. So this is minus 1. And that icky denominator turned out to be really nice by getting rid of this. And now I'm left with the limit as x approaches 0 of x over x times the square root of x plus 1 plus 1 all over x. And now my domain issue gets taken care of, and I'm left with the limit as x approaches 0 of the square root of x plus 1 plus 1. And now I can use substitution, and I get the square root of 1, which is 1, plus 1 is 2. All these limits seem to have the answer of 2, which is hilarious. All right, 4 more. We can do it. 17. The limit as x approaches 0 of absolute value of x over x. Now this is one I can't use fancy algebra to do. I can't substitute, but I would really like you to look at the graph, to consider the graph of this, okay? And it's a piecewise in disguise, basically. So I'm going to say f of x is equal to absolute value of x over x. F of x is equal to it's going to be x over x when x is greater than 0. And it's going to be the opposite of x when x is less than 0. And x can't ever be 0 because I have a 0 in the denominator. Okay, so if I simplify this, I get it's going to be 1 for x greater than 0 and negative 1 for x less than 0. And if I were to look at this graph, helps if I stay within the lines here. If I were to look at this graph, it's going to be 1 when I'm greater than 0, and it's going to be negative 1 when I'm less than 0. Okay, so as x approaches 0, now this doesn't give me a left or a right side, so it means from both sides. But guess what? I approach different numbers from both sides, so this limit does not exist. And we're going to have to justify that by saying since the limit as x approaches 0 from the left. Now I have defined this as f of x here, so I can use f of x is not equal to the limit as x approaches 0 from the right side of f of x, and I can say that negative 1 is definitely not equal to 1. So this is a classic absolute value function that's worth remembering, that it's a piecewise in disguise, and it's 1 on the right of 0 and negative 1 on the left of 0, okay? Number 18. Here we go, number 18, the limit as x approaches pi over 2 of secant x minus tangent x. Now, just from our memory, I just want you to know that the tangent graph, this is pi over 2, this is negative pi over 2, looks like this, okay? And that's pi over 2, negative pi over 2. The secant graph is the cosine flipped. So at 1, right, because the cosine would be this. If I flipped it, the secant graph looks like this, okay? So we've got this tangent and the secant graph both going to infinity, okay? But it's you can't plug in pi over 2, because if I rewrite this as what they are in sines and cosines, you get 1 over cosine minus sine x over cosine x. And if you combine the denominator, you get the limit as x approaches pi over 2 of 1 minus sine x over cosine x. And we did one like that, number 15. So I'm going to refer to number 15. And remember, what did we do? We had to multiply by the conjugate. And we got the limit as x approaches pi over 2 in the numerator of 1 minus sine squared x over cosine x times 1 plus sine x. And we couldn't plug in pi over 2 because it would give us a 0 in the denominator here, okay? And then we changed the 1 minus sine squared x, to cosine squared x, cosine x, 1 plus sine x, eliminating one of the cosines in the numerator and totally eliminating it in the denominator. And then we get cosine x over 1 plus sine x, and now we can plug in 0, and we get 0 over 2, which is just 0. Now what's interesting is as x approaches pi over 2, this should really be from the left side here. I need to change that to left side. For that limit to make any sense at all, because it does not exist if you're doing it from both sides, okay? So I need to change that to the left side. But what's interesting is that this is infinity, basically, minus infinity, because they're both going to infinity. All right, that's a subject for another time. All right, 19. The limit as x approaches pi of secant x, can I write? Secant x plus 1 over tangent x. Okay, so now the tangent of pi, believe it or not, this is pi, is 0. So I can't plug it in the denominator, but we're going to use the conjugate again, because we have some really powerful identities in trig that help us out. And so I'm going to get secant squared x minus 1 in the numerator over tangent, whoops, I have to have my x, times secant x minus 1. And secant squared x, believe it or not, is one of the Pythagorean identities, and that equals tangent squared. You're right, I heard it. Tangent squared x. And we get tan x, and then secant x minus 1. And I can eliminate the tangent in the denominator by canceling it with one of them in the numerator, and I'm left with the tangent on top. So we get x approaches pi of tangent over secant x, secant x, I'm trying to put a pi in it already, minus 1. And the denominator here is not 0 because the secant is negative 1. So this is going to be 0 over negative 2, which is just 0. And that's because, this is negative 1 here for the secant. All right, last one. 20. The limit as x approaches 0 of sine, whoops, helps if I can write, sine squared x over x. Now I'm going to rewrite this. The limit as x approaches 0 of x, getting tired, sine x times sine x over x, because I can bust it up. And I know that this limit is 1. The limit as x approaches 0 of sine x is now going to be 0 because the sine of 0 is 0. Okay, so we try to look for sine x over x when we can, which is really nice because that limit as x approaches 0 is 1. All right, so that's what we got today for the classwork limits package. And I just wanted to make sure that I had a video out for everybody to see how to work these. Thanks.